There's a place on Earth where the rules of biology seem to bend, where crabs grow as large as dinner tables, where worms stretch longer than buses, where jellyfish trail tentacles that could wrap around a 10-story building. This is happening right now in the deepest parts of our oceans, places so remote that we've sent more people to the moon than have visited them in person. And down there, in that crushing darkness, something extraordinary occurs. Something that violates everything we think we know about how large animals should be. Scientists call it deep-sea gigantism. And to understand why, we need to descend past the sunlit surface, past the last rays of blue-green light, down into a world of permanent midnight. At just 200 meters, the pressure is already 20 times what you experience on land, enough to crush a styrofoam cup to the size of a thimble. At 1,000 meters, we enter the bathypelagic zone. No sunlight, no seasons, just freezing water and pressure that would compress your lungs to the size of golf balls. And yet, life thrives here in forms that seem impossible. Take the Japanese spider crab with leg spans nearly 4 meters wide, large enough to embrace a car. Or the giant squid, the creature that haunted sailors' nightmares, eyes the size of dinner plates, tentacles that can reach 13 meters. How does something so enormous survive in a place so empty? This is the paradox at the heart of deep-sea gigantism. And the answer is more bizarre than you might imagine. Let's start with what seems like the most obvious explanation, the pressure. At extreme depths, water presses down on you from all directions. At 4,000 meters, that's roughly 400 times atmospheric pressure, the equivalent of having 50 jumbo jets stacked on every square inch of your body. For decades, scientists believed this crushing force somehow caused gigantism, that bigger bodies were better equipped to handle the squeeze. But when researchers actually tested this theory, it fell apart. Because pressure, it turns out, affects all living tissue equally. Large or small, your cells experience the same crushing force. Size offers no advantage. In fact, it should be a disadvantage. Larger bodies require more energy to maintain, more food to sustain, more oxygen to fuel. And in the deep sea, where food is so rare that some zones are called ocean deserts, being large should be a death sentence. So what's really going on? The answer lies in something scientists call Kleiber's law, a strange mathematical relationship that governs metabolism in almost every living thing on Earth. Here's how it works. When an animal doubles in size, its metabolism doesn't double. It increases by only about 75%. Larger animals, pound for pound, need less energy than smaller ones. An elephant doesn't need twice the food of an animal half its size. It needs far less. Its metabolism is slower, more efficient. And in the deep sea, where every calorie is precious, where meals are separated by weeks or months, this efficiency becomes survival. A giant isopod, the size of a football, can go 5 years without eating. Its metabolism is so slow, so finely tuned to scarcity, that it simply waits. But this raises a larger question. If being large is so efficient, why isn't everything in the deep sea gigantic? There's another force at work down here, one that's invisible, but shapes everything. Temperature. At 4,000 meters, the ocean is locked at 2 to 4 degrees Celsius, just above freezing, constant, unchanging for eons. And cold water does something strange to living cells. It slows them down. In warm water, molecules move fast. Cells divide rapidly. Metabolisms burn hot. But in the deep cold, everything becomes sluggish. Cellular processes drag. Growth rates plummet. And here's where it gets interesting. Because deep-sea creatures grow so slowly, they don't stop growing when they reach adulthood. They experience what biologists call indeterminate growth. They keep getting larger year after year, decade after decade, as long as they survive. A Greenland shark, which hunts in the deep Arctic waters, can live for over 400 years, longer than the United States has existed as a nation, and it never stops growing. The oldest specimen ever found was estimated to be 512 years old. It was born before Shakespeare wrote his first play. Imagine that, an animal that was already swimming when the Mayflower landed, still alive today, still growing, somewhere in the dark. But temperature alone doesn't explain everything. Because in the deep sea, there's another problem: oxygen. Cold water holds more dissolved oxygen than warm water. That's true, but in the deep, where there are no currents, no mixing, that oxygen is finite, limited. And here's the strange part. Larger animals have a smaller surface area to volume ratio. That means they need proportionally less oxygen to survive. Their massive bodies paradoxically make them better suited for low oxygen environments. Scientists tested this with giant amphipods, shrimp-like creatures that can grow to the size of a shoe. When researchers raised them in oxygen-poor water, the largest individuals thrived, the smaller ones died. What we've discovered is this. The deep sea isn't just allowing creatures to grow large, it's selecting for it, punishing the small, rewarding the giants. Let's talk about what's actually down there. The giant tube worm living near hydrothermal vents can grow 2.4 meters long, nearly 8 feet, and live for over 250 years. It has no mouth, no stomach, no digestive system. It survives entirely on bacteria that live inside its tissue, converting chemicals from volcanic vents into energy. The colossal squid, even larger than the giant squid, with hooks on its tentacles that rotate like can openers. Eyes the size of basketballs, capable of detecting the faintest bioluminescent glow in absolute darkness. The giant isopod, which looks like a house cat-sized pill bug and scavenges the ocean floor for whale carcasses. When it finds one, it gorges, eating so much it can barely move, then fasts for years. And then there's the truly alien ones. The big fin squid, filmed only a handful of times with tentacles that dangle like spectral threads, some measuring over 8 meters long, drifting motionless in the current like some living nightmare from H.P. Lovecraft. We don't know how it hunts. We don't know how it reproduces. We don't even know how common it is. Because here's the thing. We've explored less than 5% of the ocean floor. The deep sea covers more than 65% of the planet's surface. That's an area larger than all the continents combined. And every time we send down a submersible, we find something new, something impossible. In 2023, researchers discovered a species of sea cucumber over a meter-long living at depths we thought were too barren to support such size. What we've mapped of the deep ocean is less than what we've mapped of Mars, which means the giants we've found might only be the beginning. So we know how deep-sea gigantism works. Cold temperatures, slow metabolism, high oxygen, low predation, indeterminate growth. But there's something scientists still can't fully explain. Why does it only happen to some species? Not every deep-sea creature is a giant. Many are normal-sized. Some are even smaller than their shallow-water relatives. Why do certain groups, crustaceans, squid, tube worms, seem prone to gigantism while others never grow large at all? What determines who becomes a giant? Some think it's genetic, others believe it's ecological, but no one knows for sure. And then there's the question, how large can they actually get? We thought there was an upper limit, but we keep finding exceptions. In 2021, researchers found a siphonophore measuring 46 meters long, longer than a blue whale, one of the longest animals ever recorded. How many others are down there? The deep sea is the largest habitat on Earth, and we know almost nothing about it. Deep sea gigantism is a reminder that Earth is still wild, still unknown, capable of producing life that seems to belong to another planet. We don't need to travel to other worlds to find alien life. We just need to look down, into the crushing dark, where the giants wait. Beneath those waves, in the cold and the pressure, creatures are growing, and the deeper we go, the larger they become.